This brief video introduces the concepts of impulse and momentum just at the beginning of our linear momentum unit. We'll start by considering, like we very frequently do, a mass acted on by a force. Now, in the past, we might use Newton's second law to analyze the motion that would be changed as a result of that. In just quickly deriving the expression we're going to be using, we can see that acceleration can also be written as a change in velocity over a change in time. And if we then multiply both sides of the equation by delta t, on the one side we get this f delta t term, and on the other side we get this m delta v term. Now expanding that delta v, that would be a change in velocity, and if we then sort of distribute the m, we would get this expression. The shift in thinking is to see that the final doesn't just apply to the velocity. This final right here doesn't apply to just the velocity, but rather the entire product mv. And so what we get is on this side, the f delta t appears to be equal to a change, initial to final, in this thing called mv. So on this side, apply a force for a given time, and it changes a thing called mv. And that's a really good time for us to introduce this thing mv as the linear momentum. Now, we call it the linear momentum. It is also very frequently just called the momentum. The distinguishing linear term would be to differentiate it from rotational or, as we call it, angular momentum, which we'll see later on in this course. But this thing, mv, the product of m and v, is a new idea for us called linear momentum. Really briefly, just to explore that, what it means, how to calculate it, units, etc. So if I were to multiply this m and v for 2 kilogram mass traveling at 4 meters per second, we could pretty easily do that calculation. People find momentum to be a very easy calculation to make. The idea is conceptually challenging. It's mathematically very easy. But as we progress in the unit, you'll notice what you'll discover is that it's kind of an abstract concept that can be really tough to wrap your head around. So there's the easy calculation. We can consider the units, and the units just come out of the calculation. They're kilogram meters per second. You might think there's actually kind of a special unit we call, if in the past, if these things came up, we might have had a derived unit, but in fact the units for momentum just remain kilogram meters per second. A really important idea, and maybe a central important idea to this, is that this is not just a math problem. This is actually a vector multiplication problem. So velocity is a vector that's being multiplied by a scalar to give a vector. So this thing here is a momentum vector, and it is in the same direction as the velocity. So we can describe this traveling with a momentum vector, and that's really a big idea. So back to where we were, now that we've introduced this thing, we can continue writing this derivation down. We could see that f delta t produces a change in this thing called p, or momentum. And then sometimes it's just written like this, which is just applying the definition of delta. This is very similar to the equation that is on your equation sheet. I think it's actually reversed right to left, but this expression is on there. What we just wrote here is known as the impulse momentum theorem. Now, this is not actually saying that impulse and momentum are the same thing. Sorry, impulse and change in momentum are the same thing. It's actually saying that the impulse is one thing and the change in momentum is another thing, and that they are numerically equivalent. This side here, the product of f and the interval, is called the impulse. This side here is technically the change in momentum. So if it was being properly named, it would probably be called the impulse change in momentum theory, but it's called the impulse momentum theory. Impulse sometimes has a different letter given to it. It actually has its own letter, J. So sometimes you'll see this written as J equals delta P. That really has no use for us in this course. It's written like this on your equation sheet, but you should know if you were looking at other sources, you might see this J, and these are the same thing. Don't ever forget that it is a impulse momentum vector theorem. And what this is saying, this is really kind of a key idea, is that the direction of the force is the same as the direction of the change in momentum. The momentum changes in the direction of the net force. And that's just the other way to say it down here. So how does this fit into what we've been doing? Well, we now have kind of a third model that we're going to use. The model we've used so far is like dynamics, and you would add kinematics, and then work and energy, and now we have impulse momentum. And it's really fun to consider the cause and effect and how we use the words in each of these. In the case of dynamics, we say forces cause acceleration, which is the effect, and we can see that as a change in velocity. Connecting these two, we might call a dynamics problem. Connecting these two, we might call a kinematics problem. Both are, but that would be the the dynamics kinematics approach. In work and energy, we knew that work was the cause, and changes in energy is the effect. Work causes a change in energy. Work changes energy. With impulse momentum, impulse would be the cause, and I'll address what do I mean by cause in a minute. And a change in momentum is the effect. Impulses change momentum. By the cause, I kind of am talking about this idea of force. Work occurs when we apply a force through a displacement. Impulse occurs when we apply a force for a given time interval. But when we apply work through a displacement, we change energy. When we apply a force through a displacement, we change energy. When we apply a force for an interval, we change momentum. These are two big ideas, and we can use them as kind of different lenses to analyze different problems. And we're going to talk a lot about when you would use it, etc. But this is work and energy, a scalar approach to solving problems. Impulse and momentum is another vector approach similar to dynamics. I'm going to just briefly show the three approaches for a relatively easy problem that we've encountered several times so far. So in this situation, you have a mass of 2 kilograms, maybe the one we were talking about earlier, traveling at an initial velocity of 4 meters per second, at which time it is acted on by a force. In this case, the force is the unbalanced force. We'll call this whole thing the net force. And this force is going to act on it for 2 seconds, and we might ask, what's the final velocity? So just going to show how this would be done in 3 different approaches. In a dynamics and kinematics approach, you guys know what you would do. You would take a sum of forces statement, and then this is the algebraic expression that yields the acceleration. If we solve for that, we would of course expect to get an acceleration of 5 meters per second squared. That's the dynamics problem, the Newton's second law problem. Then we would look for a kinematic expression, one that relates the final initial velocity through the acceleration. And we find that this is an initial velocity. The acceleration, this is technically a delta v term. There's a delta v of 10 meters per second, and the final velocity then is 14 meters per second. In a work and energy approach, we always think, what's the initial kinetic energy? How much work was done by this force? That's this. And then what's the final kinetic energy? So expanding those 2 variables we have, you guys know this is the kinetic energy. You know what force is, and kinetic energy. The issue here is that we don't really have a displacement right now. So you would go ahead and, knowing this acceleration from before, do a kinematics problem to find the displacement. We would find in the 2 seconds in which it accelerated for that amount, it would cover 18 meters, and that's going to end up going in here. So now expanding this, just plugging in the numbers we have, here was the 18 meters. We apply a 10 Newton force for 18 meters. This is our unknown. I like to show it like this, kind of showing, these things have physical meaning. It had 16 joules of kinetic energy prior to 180 joules of work being done on it, and then we see that this would be now the final kinetic energy would be 196 joules, divided by this kilogram here. 2 and 2 cancels out anyway, and then we get a final velocity of 14 meters per second. So again, similar to what you've seen before. Now our new idea here, and these numbers are suited particularly well for this problem, but just like we did here, we would expand the definition of momentum to be mv, and then we would kind of plug in what we have. In this case, the impulse is right here. The impulse changes the momentum, and here it is. It's the 10 Newton force applied for a 2 seconds time interval. Our unknown then is the final velocity. We could say that our original momentum is 8 meters per second. We had 8 kilogram meters per second. We had a 20 kilogram meter per second impulse, and that'll produce the final momentum. Solving for this is pretty easy, and we get again a final velocity of 14 meters per second. It is good news that we got the same result for all of these. Seeing P equals mv might make you think that this is or can be connected to another concept we've used. Kinetic energy was 1/2 mv squared. We can take this kinetic energy expression and multiply it both sides by m, and then group the m terms here as mv. Obviously m squared v squared is mv squared, and then you see p emerge because we can define p as mv. And then just rewriting this, we now have an expression that relates P and K. And I'll use that sometimes later in the unit. Writing that in terms of P would be easily solved. Before you get to the homework, you should probably know about one really common mistake, and it comes from the idea here that it is a vector quantity. So if we had this initial situation, and then kind of sometime later, this was the initial situation, or the final situation, same mass traveling the other way, 3 meters per second. If you went ahead and did this, you need to be very careful when you expand this, and you can do this like this. You don't have to do mv and mv. You can apply the delta to the v because m is a constant. But if you lose sight, things going haywire here. If you lose sight of the idea that this is a vector quantity, you will not get the signs right. And we use algebraic signs to indicate positive or negative. So keep in mind this is a vector quantity. That means when you put this final velocity in here, we've chosen a positive direction, maybe to the right here. That means the final velocity is a -3. This velocity has changed, not by 1. The speed has changed by 1, but the velocity has changed by -7 meters per second. That's a key idea. Because when we do this, the change in momentum is a -7 times 2. And the magnitude of the change in momentum is 14 kilogram meters per second. So this is really indicating the size of a vector, and this thing, a force applied through a time interval changed the momentum 14 kilogram meters per second, and it changed it in that direction.